Good morning, my dear students. Last session, I have introduced the structural analysis to subject, its syllabus and the regulations and the course outcomes and how they are mapped to program outcomes. Then the course and survey form that each and every student at the end of the course that he has to assess himself for the purpose of assessment. And now today, in this session, we will talk about Unit 1 of the Structural Analysis 2 syllabus as per JNTUK. It is three hinged arches. Right, these are the topics that we are here to discuss. Firstly, elastic theory of arches, then the theorem which the arch satisfies, that is Eddy's theorem. The determination of horizontal thrust, bending moment, normal thrust, and radial shear, nothing but the internal forces developed in the arch. Then the effect of temperature on the three hinged arches. Then the analysis of the arches with hinges at different levels. Let us see some of the examples of how arch really looks. You might have seen many of the arches when you visit monumental places. The olden structures, age-old structures, the arch shape is very common. They might have been built in brickwork or maybe the stone masonry. They're very very much familiar to you when you visit the ancient structures. In modern times, as we have now we are using steel and concrete very much into the construction. So I present to you some of the arch examples of the pictures of arches, particularly three hinged arches made of concrete. The one which you will see now is the Rosgraven Bridge in Switzerland, which is a three hinged arch which is built in RCC. So you can see there is a hinge in the middle and the two hinges at the ends. So this is a three hinged RCC bridge. The other view of the same bridge, where you clearly see the central hinge. Generally, the hinge is very common in steel structures, but how we do provide the hinge in concrete structures? These are the different types of hinges that are possible with concrete, which is the saddle bearing is the one type of it, and lead sheets can be used, or Fressinet hinge can be formed, or Masnager hinge, or consider hinge can be the option for hinge creation in concrete. And this is another one, another example of three hinged arch where the hinge, the middle hinge can be seen, which is a steel bridge. It's a Ravenna Park bridge in USA, which is three hinge steel bridge. Similarly, you can see the hinge at the end of the arch, the same bridge. The hinges, which three hinged arch consists of hinges at the supports and hinge at the top. So there are three hinges in the structure, so which is steel again. So this is the some of the pictures that I present to you for a clear idea what exactly a three hinged arch practically. Now let us see the exact meaning of what is an arch and how it is different from the beam and the purpose of construction of arch. So you can see in case of beams supporting uniformly distributed load, the maximum bending moment increases with the square of the span, and hence they become uneconomical for long span structures. For example, if you take a simply supported beam with a uniformly distributed load, the bending moment is at the middle is WL square by 8. W being the UDL value and L being the span. So WL square by 8, where you can see L square in the value. So if the span is increasing by twice, so the bending moment increases by 4 times. So this is what does that mean? So the maximum bending moment increases with the square of the span, and hence the long span structures, the beam option is uneconomical. What do we do if the span is large? So in such situations, the arch can be employed, which is advantageous. How it is going to be advantageous? We will see that the arch will develop horizontal reaction. That is a prime reason to reduce the bending moment. Uh, the beam, when you say beam, we will have vertical reactions at the supports and no horizontal reaction. Whereas when you come to arch, the ends of the arch are hinged. Hence, we expect horizontal reaction when the gravity loads are applied on the arch. That horizontal reaction will bring down the bending moment developed in the arch. This is an example taken for comparison how beam and arch are different in case of developing bending moment, because bending moment is the prime concern for design of a structure of an element, structural element. The prime design parameter, the important design parameter is the bending moment. So uh, there is an arch taken, which is just an example. We have a load P, point load P, applied at the L by 4 distance from left, and if you can see, the reactions are left vertical reaction at left support is 3p by 4, and the vertical reaction is p by 4. So if it is a simply supported beam, the bending moment below the load, if we go back to the picture again, the bending moment under the load is nothing but 3p by 4 into L by 4 if it is a beam. So it comes to 3pl by 16. So that is what is given there. Now consider the arch with the same load. Now if you work out the bending moment again, now you can see that if you take bending moment about the point where the load is applied, so 3p by 4 into L by 4 is going to be clockwise, which is 3p L by 16, and h into y is going to be anti-clockwise. So which means the bending moment below the load is 3pl by 16 minus h into y. So the arch option is reducing the bending moment, which is actually 3pl by 16 in beam. So how much is the reduction is nothing but horizontal reaction that the arch is having, and the y is nothing but um, the height of the point that is taken for bending moment calculation, or the ordinate of the point along the arch. So this is how the bending moment in uh, arch is going to be reduced. So the option arch is having the advantage of reducing the bending moment. Now coming to the shape of the arch, which shape of the arch is going to be a perfect shape? We will come from the cable. So let's take a cable. When you load the cable, the shape of the load and no, the cable takes the shape of the load. Right now, let's come to the shape of the arch. So cable takes the shape of the load, and this shape is termed as funicular shape. So we will discuss extensively when we deal with the cables and suspension bridges. So for now, you understand that the when you apply some load on the cable, the shape of the cable depends on the load applied. That is what we call the funicular shape, the shape attained by the cable when you load it. If you just invert it, that is going to be the arch. So inverted funicular is the shape of the arch, perfect shape of the arch. So if an arch were constructed in an inverted funicular shape, it would be subjected to only compression, and there won't be any bending moment in the arch. Bending moment will be zero. So this is what is the uh, perfect shape of the arch. But practically, to arrive at the funicular shape is not possible, and the load that you apply on the arch is different from the load that is expected for arriving at funicular shape. Hence the arch will have bending moment in the arch. Okay, so in addition to compression, we will have bending moment also in the arch. As arches are subjected to compression, must be designed to resist buckling also. It's very common phenomena. Even you might have studied in dealing with the columns. Slender columns uh, will come across this concept of buckling. Right. Um, uh, until the beginning of 20th century, arches were commonly used to span between walls, piers, or other supports. Now, the modern times, we will use arches for bridge construction majorly. And the earlier arches were constructed using stones and bricks, as I was telling. When you visit any ancient structures like monuments, then you see only either brickwork or masonry work, stone masonry work. So in modern times, we use RCC and steel, as I have shown you some pictures of it also. Right, now comes to what exactly an arch is. How do you define the arch? It is not based on the shape. Anything curved in vertical plane is called as arch. It's not going to be okay, because you can see it is depending on the supports, the load that it supports. That is where we need to concentrate on, not on the geometry. So you compare the two figures, figure A and figure B. Figure A I named as arch, and figure B I named as beam. The reason behind this is, figure A, there are some horizontal reactions shown, whereas figure B, there is no horizontal reaction developed. So that's the prime concern for us when we differentiate arch and beam. So beam will not have any horizontal reaction, whereas arches will have horizontal reactions. So it is important to appreciate the point that the definition of an arch is a structural one, not a geometrical one. Just by looking at the geometry, you can't say this is an arch. Then what are the types of arches that are commonly used in practice? There are three hinged arches and two hinged arches and fixed arches. A three hinged arch is a statically determinate structure, and its internal forces can be evaluated by equilibrium equations alone. So this static indeterminacy is already introduced to you in structural analysis 1, wherein we can differentiate the determinate and the indeterminate structures by calculating the degree of static indeterminacy. So by counting the number of unknowns present in the structure and the number of equations available for solution. So if they both are not same, then if the number of equilibrium equations are not sufficient for the analysis of the structure, we say it is indeterminate. So here a three hinged arch is statically determinate structure, which means without any additional equations you are able to solve uh, the forces, reactions or internal forces in the arch just with the help of equilibrium equations. Whereas two hinged arch and fixed arch are statically indeterminate structures, which means to solve them, in addition to equilibrium equations, you need to use additional equations. That is what it means. So the two hinged arch and fixed arch are statically indeterminate structures. These are some of the pictures that are depicting the types of arches. First one is a three hinged arch, and the second one is being the uh, two hinged arch. This one, and this is two hinged arch, and you can see fixed arch. And one more type I have listed here, which is not enlisted earlier, which is called single hinged arch. So for a fixed arch, if you have a hinge at the crown, it's called crown point, where if you have a hinge here, we call it as single hinged arch. So these are the types of arches. So earlier we have shown that the arch is economical just by taking some example of load with arch and beam comparison. Now we'll do it with not qualitative analysis. We will do quantitatively what exactly is the difference in bending moment when compared to beam, the bending moment developed in the arch. Okay, so let's consider a three-hinged arch subjected to a concentrated force which is applied at L by 4. Total span of the arch is L, then rise of the arch is H, is the rise of the arch, the span of the arch, then the crown point is called crown. These are called the springing points where the abutments are there. Right. Now comes to the calculation of bending moment in arch. Okay. Let us see. First, we need to solve for external reactions, which are the vertical reaction and horizontal reaction at A, vertical reaction and horizontal reaction at B. So there are 4 reaction components here, as you see, but you have 3 equilibrium equations possible. So there is one more unknown left to solve. Hence we take the equation, the condition that the bending moment at the hinge is 0. That is a condition. So that we will utilize here for solving this the reactions, external reactions. So let's see. Taking moment of all the forces about hinge A is just a regular procedure of solving for external reactions of any structure. So we will use equilibrium equations. Sum of moments about any point is 0. Sum of vertical forces is equal to 0. Sum of horizontal forces is equal to 0. These are the equilibrium equations that we use for solving external reactions. So now I am using moments about A. So taking moments about A, so it will be RB into L and P into L by 4. Okay, so RB into L, P into L by 4. So this is what is here. So RB into L is equal to PL by 4. So that is written as PL by 4L, which is nothing but P by 4, means the reaction at B, vertical reaction at B is P by 4. Then using sum of all vertical forces is equal to 0 equilibrium equation, we will have reaction at A 3P by 4. Right, now taking moment of all forces to the right of the hinge, about the hinge C. If you see, we need to use the condition that the moment at this hinge is 0. So taking moments of all forces at this hinge C. So there are two forces to the right of C. RBY into L by 2 and H into H suffix B, so horizontal reaction into the rise small h. So this is what we need to write as moment. You can see it here. H into horizontal reaction at B into the rise value and RB into L by 2. So that will give you horizontal reaction where RBY you can substitute from the earlier calculation, which is P by 4. So that will come PL by 8H. So this is horizontal reaction. So at B, then applying sigma Fx is 0, that gives you HA is equal to HB. That means horizontal reaction is same at A and B. So that is PL by 8H. Now bending moment below the load is given by this. Okay, so bending moment below the load, I need this point. So RAY into L by 4, then H into B. Okay, this is the value. So this is what we write for bending moment at the RA into L by 4 minus horizontal reaction into B. So we substitute for different values. RAY we know the value, this is 3P by 4, and we know HA value PL by 8H. So all this we substitute. So for a case of B by H 1 by 2, we'll have bending moment at point load is 0.125 P into L. If the same problem, we replace this arch by a beam, the same load, same span, all that. So what will be the bending moment at point load under the point load is 3PL by 16. So vertical reactions will never change because we have not changed the load position. So reaction at A is 3P by 4 into the distance L by 4. That is the bending moment at this point. If it is a beam, we need bending moment here. So RAY into L by 4. No H will be present when it is a beam. Horizontal reactions are absent when it is a beam. So moment at D, if it is a beam, it is 0.375 PL. If you clearly see the two values, it's arch option, beam option. For the same span, same load and all. So when you employ the arch, the bending moment is going to be 1/3 of, if it is a beam, 1/3 of the value if it would have been a beam option for you. So you do this 1 by 3 for this, you get 0.125. Other way, the bending moment is reduced by 66.66%. Right, let's see what is elastic theory of arches. Nothing but in the other way, what is the theoretical arch, which means the arch which will have only compression in the arch, bending moment is 0. This is what how we are going to uh, construct a theoretical arch. That let us discuss. So Let's consider an arch with loads as shown in the figure. This is where this is an arch with the loads, some loads on it. Um, Now represent the vertical loads to some scale on a vertical line. This is where it is shown here. So you draw a vertical line. For example, load W1, say it is 100 newtons. So the length of AB is scaled such a way that it is 100 newtons. Means for example, 10 newtons is 1 centimeter. Likewise, you take some scale, draw W1. Similarly, W2, according to the value, you draw BC as W2 load. Similarly, CD as W3 and then DE. This is how we represent the vertical loads to some scale on a vertical line. Then you select a point outside vertical line at some distance. This is what the point is. Select a point outside vertical line at some distance. That is done. Right. Join this point with all the points, salient points on the vertical line, that is A, B, C, D, E. Right. So now draw lines parallel to OA, OB, and etc. on the arch. This is now you take the arch, the loads given. Now you draw line parallel to OA starting from capital A. So this is a line parallel to OA. Then draw line parallel to OB. This is a line parallel to OB. Draw a line that will intersect with the line drawn parallel to OA. So this point is an intersection point, and from here till this point, this is what is the compression compressive force in this portion. Similarly, the compression in this portion, then compressive force, and then compressive force. So this is how we get the compressive forces in the arch. So these are all it's like a number of lines, a network of lines. It's a polygon. Um, um, okay, so such polygons can be drawn by choosing this point anywhere. So if we pick the point over here, we will get a different network of lines. So likewise, you will have a number of polygons are possible. So which one is the funicular polygon? Which one is the polygon which is exactly suits to these loads, which will develop only compression in the arch? That is what is called funicular polygon. So that is nothing but funicular polygon which lies within the actual arch is called as line of thrust. So this how do you get the funicular polygon? So by choosing O, it's a trial and error. So by choosing O, so we should get the network of lines lying within the actual arch. This is the actual arch. What is drawn here? This is the actual arch, and this is the theoretical arch that we try to draw each time when you pick a point O. So there are a number of such polygons can be drawn. So the exact one which can uh, which can be laid in within this the actual arch. So that is what is called funicular polygon. So polygonal arch following the path of the true compression is called theoretical arch, the other way called as linear arch. Okay, so this is the elastic theory of arches. Okay, thank you all. We'll meet in the next session.